Hi, my name is Bob Grenier, and I'm a volunteer with the Martin Fleischmann Memorial Project. So welcome to this O-Day, Flower of Life 2. This 14th of September 2025. I hope everyone is well out there. Hi, Green Hiker, EBB, Craig, Nathaniel Hanks, Gordon Doherty is in the house, Corky Goss also, Mika Avila, see you soon, Nathaniel, Philip Demois. Pleasure to have you here. Paul Keen Music. Rotas over there in Australia's. Ken Pratt also. Hi, Mark Alexander. And thank you for your donation, P. Atlantis. Hi, Misunderstood. Hope it's not too late for you now. And hi, Todd Hall. Hi, Omega and Wayne. Toroidal Soup. MEF. Sebastian Sosnowski. Overwound Games. Hi, Nick Knock. Welcome, one and all. We have a good quorum, so let us begin. So, I have been working diligently and doing research in a number of places in the world. And one of those places was many moons ago, actually, and it was in Morioka in Japan, where I presented a poster on what I thought was the whole process of Lena, and we are going to discuss more evidence that points to this. And what have I got on the screen here? Well, this is a Shinto temple. In the background there, it's part of a Shinto temple complex. The Shinto faith was polytheistic and animistic in its kind of foundation. And it's a faith for the indigenous folk of Japan. And it focuses on kami, divine spirits and powers found in nature and in significant people. Apparently began during the Yayoi culture. I'm sorry, I'm probably saying that wrong. Somewhere between 300 before Christ and 300 Anno Domini. What you're looking on the screen here is a lion dog, as we say in English, or a komainu. Originally, these came across from China. And actually, the first one I saw, I have shown before. In fact, I showed it in my O-Day Flower of Life 1, which I had the pleasure of touching when I was just a wee lad at 18 in Beijing, in the central temple of the Forbidden City. And it's the right lion dog, foo dog. And it had what looked to me, a large ball lightning structure, a large Flower of Life spherical object under its right paw. It was on the right as you go in. Now, it was oriented towards you as you went up the stairs. These dogs actually are from India. They have a lion's head and a dog's body. And apparently the first lion statue that is dated was from around the 3rd century BC. So actually around the same time as the Yayoi culture. And it was on the top of a column and it was erected by King Ashoka. Hello, Mad Hatter and Starfish Troopers and Andre Valentine. Great to have you here, Pyro Pedals and Mr. Gate Mode. Wonderful Martin Angel. Excellent. Yeah, so you may have noticed that I might have taken this photo because of not this. This is the head. And as you can see, we have a vortex for one eye and a counter vortex for the other eye with a central structure, which is a sphere. Slightly ground off, probably from the original stone, maybe. And then you have the cone going into this central sphere, which is the nasal passages of the lion dog. For me, this is extremely indicative of the technology that runs the universe. And it's no wonder it's such an important symbol. These dogs, these lion dogs, they protect the Shinto temple. Now, you may have noticed it, but under his left paw, he had a very miniaturized version, in my view, of a ball lightning-like structure with the flower of life on it. And I think we can call this a micro ball lightning compared to the one under the dog, which I showed you in my O-Day Flower of Life 1 presentation. Actually, the first time I showed that was in Sochi in October 2018 to the Russian community there. Now, just behind this lion dog, there is the roof of one of the temple buildings. And north and south, it has these wonderful carvings. And this is the north-facing one, as far as I know. And this central point, I think, is rather lovely. And why do I say that? It's because you can imagine this as a model of a topological monopole with 6 divisions: vortex and anti-vortex, vortex and anti-vortex, vortex, anti-vortex. Now, this could be a north pole, strong pole facing into the center, or a south strong pole. If it was a north strong pole, this would be a north beam. And if this was the south strong pole, this would be a south beam. And this is effectively the Boyd-Bushman, Lockheed Martin directional magnetic beam patent here on this temple. So there we have it. Really rather lovely. One is facing north, the other one is facing south. How very, very interesting. I've got a really big close-up here, so you can really see the detail in the wood carving. Rather beautiful, wouldn't you say? The shrine here, Witch Doctor, is in Akita Prefecture, where the Shiba Inu dog comes from, of course. Shiba Inu dog looks a little bit like those dogs that they have at the front of the Shinto temples. Yeah. So earlier today, I shared for the first time one of the videos that I took in March 2024, looking at the pipes of Binjuan Huang's reactor, specifically I think the DH2 pipe, DHX2 pipe, one of the ones that produced more excess heat. And here are 2 images from some of those reactor core pipes. This is from an inner collapsed pipe, and you can see these florets with quite intense numbers of platelets around their perimeter. And then this is from the inside of the outside. And again, you can see these florets. Now, typically these florets are buried kind of 50% in, either directly into the surface, or approximately 50% in at an angle. So this one's directly in and this one's at an angle. These 2 are both at an angle. I suspect in both cases these were pairs themselves. So one was a pair of the other in both cases. Now, when you look at these structures, other than the ones that are completely broken up, you can see various levels of intensity of and density of material in the vortex spiral material that is accreted to the outside of what we established was the apple part of the magnetohydrodynamic structure. The interesting thing is, it became very clear that the outside of this is extremely powerful, and it must be for it to burrow in here and for it to burrow in here. But one example we showed in the poster in Morioka was this one, and it's actually the image on the right, where you can see a whole bunch of these structures buried variously into the copper pipe. But the most interesting part of this frame is where a pair had crashed down on here, and they'd sort of scraped along the surface and then one had separated and come down here, and in fact it's gone down here. It's actually smashed through a couple more that were already on the surface and carried on and gone off the frame and down here. But the other one of the pair stopped here. And so I blew that up, and you can see here the structure that came to its rest at this point. And the most amazing thing about this is that you have this wavy cut. And this is essentially pure copper. And given the fact that this is 20 microns across, let's say that is 2 microns, that would be 1 micron. Thank you very, very much, Craig. That's really appreciated, that $50. This is 1 micron. And so this is nanometric in scale. I estimate this to be around about 90 nanometers, certainly no more than 200 nanometers. So whatever it is, the outside of this dying magnetohydrodynamic structure, it was able to scrape off a layer of copper, and it was starting to swirl around it. And it's also, not only is it scalloped here, but it's also scalloped here in like one scallop there, one scallop there, one scallop there. You can see my mouse if I shake it. I'm over here. I'm talking about these waves and then the waves down here. And that kind of mirrors what you see on here. You actually have these kind of like platelets that come out like this, but they're also, not only are they layered like this, they're layered up like that. So what this tells me, and this is going to be very important as we go through this presentation, is that the structures themselves are able to capture material from the outside of themselves. Now, in this one, you can see how the structure has its tornado coming down from the bottom of it, and it's touched down here like a tornado does in, you know, Midwest of America. And it's starting to interact and suck up copper and oxygen, copper oxide here. And it's pulling, as it's pulling material up, it has a moment on itself, and it's pulling that structure into the copper pipe. And so it eventually crashes in, having pulled itself down. So not only are we able to capture material on the outside, we are also able to capture material from the tornado that comes out. Now, when the music stops and the thing spins down, the material that is, in my view, coherent matter inside loses the magnetohydrodynamic, specifically fractal magnetohydrodynamic structure that is able, through the topological monopole, to cohere matter into the phase singularity, which is the topological monopole. And so the coherent matter in the core is then thrown out, or it expands, but it's still spinning. And so this span out into a tornado and expanded. And as what I would consider a quark-gluon plasma hits the ordinary vacuum pressure, because it was a different vacuum state in here, it was a false vacuum in here, different parameters like the dielectric constant, the physical vacuum was different in here, and also it's coherent, and the photonic pressure is different in there. When that vacuum state, control of that vacuum state collapses because the fractal magnetohydrodynamic structure spins down, then the matter is coherent matter in the form of electron quark-gluon plasma is spat out, and it hits the ordinary vacuum state and freezes instantaneously into a range of stellar synthesis elements. Okay, principally hydrogen, carbon, and oxygen. Okay, so this supports the hypothesis of abiogenesis of hydrocarbons. And here are some more examples coming out of this little hole, this whole conglomeration coming out of this little hole. And as you saw in the presentation that I shared earlier today, if you saw it, if you haven't, go and see it, and in previous analysis of these materials, essentially the background, and you'll see this in a minute, is basically copper and oxygen with some small amounts of carbon. That's predominantly all it is. The carbon is produced profusely by these structures, and so it's not surprising there is some carbon on the copper, and there will also be carbon around. But what I love about this kind of system, where you have one heavy element in the background and the matter is born, you can see exactly where the matter is coming from. You can see that all of that matter absolutely cannot possibly fit in there. You could argue the same for this, and therefore it has to be in a coherent matter state in here, and therefore something really rather non-ordinary is going on. And this is not contamination. This is produced by these magnetohydrodynamic structures. Now, sometimes it bursts out like this, but sometimes the inflation inside is too much, and the material's still spinning around, but it just expands and the outer shell is just broken off. And I believe that is an example here, where you've got mostly the body of the structure, either here, or this one, and this one has broken off, and the kind of vortex material was still going around as it froze out. In this last example here, essentially it is the entire inside, in my view, of one of these structures, which inflated, it popped off the outsides, and it died somewhere else. It has a hexagonal type structure on the top here, so one could argue that this had a 6-order structure internally to it. Okay, it might be that in water it always appears that the top level is 2, although sometimes we see 3, but the internal structure might be 6. It has to be at least 2. Now in this next one, we have one that does look like it is a 3 structure internally, although this one and this one look like a 2 and a 2, and they look like a pair. But yeah, this one, it has a distinct triangular top to it, so this may be a 3-order structure inside. But when I was working with Jan Rack and using the Sony Alpha just before I left for America, we did some imaging and used some 1/8000th of a second frame rate captures, and it changed the exposure level. And what I saw immediately looked like this that you see in front of you here. So just hold this image in your mind, and I'm going to flick to the next frame. This. And to help you, we have this. Now, of course, this is what? If this is a 5 micron scale here, this is, let's say, 10 microns across. This is, I think, at least 10 millimeters across. It might be larger. I think it might even be 20 millimeters across. And so whatever, this is much, much larger. But what you are looking at here is a magnetohydrodynamic structure. And what I believe you are seeing captured, because we are able to take a 1/8000th of a second time slice of this, is a similar structure to here, where you have a wave, and 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 there's a layer here, 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 there's a layer here. Okay? And we do know that plasma is scale invariant. So what I would argue is that this structure is a prototype of what is going on here. Nature is almost always trying to do what you see here, but As you know, when you have magnetic structures, the tighter you push them together, the more intense the field becomes. Okay? So this is trying to be a matter wave. I would argue, and I have done continuously, that this is a collapsed coherent matter wave. Okay? Now, it might be something deposited on the coherent matter wave. That is to say, material that's captured from the boundary or material that's been synthesized out and spews in. Now, we do know from the video that this spins round. And so what I would argue is that either the bottom of this is the South Pole or it's the North Pole. It's only going to be one of the two. And I believe that this is the North Pole because the South Pole will have the vortex going into it. Okay? I've got a 50% chance of being right or wrong. Someone asked, Omega says, is it a spiral? I think it actually likely is. It is a spiral. Okay? The structure that's producing the spiral is not a spiral, but it emerges out of the fractal structure. The spiral emerges out of the fractal structure. It's just natural. And why do I say that? Because if you look at the next slide, this is a 3-order structure. So I'm saying that this is a 3-order structure. We know we do get 3-order structures in cavitation processes because we saw it here on the cavitation plate of Dr. Roy Shinomasa in Japan. And we saw that it is able to burrow out triangular holes into the steel. And if I click here, you will see that carbon is on the outside because it's diamagnetic, although it will go through the core. It is coming around here and it is going through, okay? That's important because it will allow it to transmute. But of course, majority of it is stuck around the outside. But if you look at the oxygen signature, the oxygen signature is in the core. Why? Because it's paramagnetic. That also means it's in the core of the core, okay? So you can get carbon and oxygen going through here. This is very important. This is a water system. It's capturing carbon. It's got oxygen. Is the carbon made from the oxygens? I don't know. We're going to look at that later. Okay? But here in the sadly departed, Neil Crichton Gold Lion experiment, we have a 3-order structure on his copper oxide. And again, in the Vega experiment of Henk Uren, we have a 3-order structure with the Paisley, the vortex going in. Now you always get a widening beam of vortex if you have 2 or 3 structures. Much less so if you have 4, and when you get to 5 and 6, you don't. And we've explained that. Because here, this will have a beam that comes out and it will cut through the non-radiating boundary. This will have a beam that comes out. This will have a beam that comes out. This produces the vortex, okay? These substructures. And of course, they produce something that goes into the core from behind in this case. Now, this is with 3. When you have 6, you literally have the flower of life. And so this is where we were with the flower of life part 1, where we derived the structure the fractal structure that leads to the flower of life. So this is in Malcolm Bendel's thunderstorm generator. The majority of them are 6, some of them are 5. This is again in the Henk Vega experiment where we cut out a hemisphere from a copper pipe. This is on the near boundary area, and you can see 6 produces no beams coming out like you've got here, these 3 beams coming out. And it has a round hole, okay? And the reason is that the vortex goes into the apple of the structure on the loop on the way round, okay? So then you can say that these ancient Scandinavians got this quite right. Of course, I had a beef with that guy that at the Tesla Tech conference, that actor, because he was calling this part here the Vesica Pisces. And whilst it is the shape of a fish bladder, it's not the Vesica Pisces. The Vesica Pisces in the flower of life is this part. Okay? And there's 6 Vesica Pisces in real Vesica Pisces in this structure. Okay? It's not these bits. Okay? So let's have a look at what we see. This is another area where the surface seems to have been damaged, possibly by a passing magnetohydrodynamic structure. And when we look at those areas, we see essentially either pure copper or mostly copper with a little bit of oxygen. And in some places, there is a little bit of carbon. But for the most part, it is almost entirely copper or copper and oxygen, as one would expect for a piece of copper. Okay. Here in this example, we see, again, this little fleck here could be one of these but overturned. And we see that that is mostly copper and oxygen. Same for this. But when we see what I call the fat Oreos, these things here, which are one of the internal structures, the wheel within the bigger apple, we can see that this contains more carbon and it contains phosphorus. Phosphorus. Okay, that's going to become very, very important. So as we go through some of these, here is like this substructure may have come out of this breaking up, or it's just spewed this material out. But looking at this boundary in between here, this is 233. We can see here 233, carbon, nitrogen, oxygen, magnesium, aluminium, silicon, phosphorus, sulfur, chlorine, potassium, calcium, iron, copper. Okay. Again, on this area, right as it's spewing out, this little area here, 230, we have carbon, nitrogen, oxygen, silicon, phosphorus, sulfur, chlorine, potassium, iron, and copper. Okay. So we have all of these elements. And essentially what we started with in the reactor is reverse osmosis water rather, reverse osmosis water. So that should essentially be iron-free water. It will have dissolved oxygen and nitrogen and the infinitesimally small amount of CO2 by the partial pressure and a little bit of argon in there from the air. And it has copper and probably some carbon and so on from deposits in the pipe initially. Again, in this one that came out, we have carbon, oxygen, magnesium, aluminium, silicon, phosphorus, sulfur, chlorine, potassium, calcium, and here again we have the same story. We've got sodium here in this case as well. Some of these they actually had sodium, and they might have had nitrogen as well. So in this one, I've not put nitrogen here, but there is I can see there's the nitrogen peak there. Okay, because there's a peak between carbon and oxygen, and it's there. So I didn't choose it, but it's there. Essentially, this material in the center always has carbon, nitrogen, and oxygen, and there is a sodium peak here. That little thing there, and you can see I've got it here. Okay, so there is sodium in there. So essentially what we're saying is you can't, on an EDX, you can't really see boron, beryllium, lithium, and hydrogen. Okay, but given the fact that we got carbon, nitrogen, oxygen, sodium, magnesium, aluminium, silicon, phosphorus, sulfur, chlorine, potassium, calcium, and iron already, I would suggest that you will find that there will be boron, beryllium, lithium, probably helium and hydrogen in there to some degree. But we can't see those with EDX. Again, here, the product coming out. Carbon, oxygen. Let's have a look. I don't see much of a nitrogen peak in this particular one. But here we've got titanium, a clear peak on the titanium as well. So we've got another missing part of the puzzle up to the mass of copper. In this one, this beautiful kind of splay out. What have we got here on this part where it's all blended in? We have 221, 221, carbon, oxygen, phosphorus, sulfur, chlorine, potassium, iron, and so forth. This one's totally broken up. It seems to have spilled its guts here. What do we have? Carbon, oxygen, fluorine. I think that's probably nitrogen. No, the nitrogen peak isn't really there. What is this one? This is not that one. That one is 210, I think. 210. Yeah, that's one I'm looking at. It has fluorine in it. Okay, so we have fluorine as well there. Magnesium, aluminium, silicon, phosphorus, sulfur, chlorine, potassium. So we've pretty much got all of the elements up to the mass of copper. We're not seeing nickel, we're not seeing cobalt, we're not seeing manganese, we're not seeing chromium, we're not seeing vanadium or scandium, but we are seeing titanium. Not in that one though. Again, looking at the background here, just copper, oxygen, and a little bit of carbon. But when we look at the surface here, we see phosphorus coming in. Now I've done a map here. This looks like the center of something that's come out, and that is rich in iron. You can see down here, it's really large iron splodge. And then the electron beam is coming from this side, so this is all in shadow. So down here on these images, phosphorus. Phosphorus is only on the shell. It's only on the shell. Whereas copper is in the background and a little bit on the shell. Okay. In this case, we're looking at a shell here, big peak of phosphorus here, 7.62 mass percent. And because the mass of phosphorus is, you know, half that, more than half that of copper, this is actually quite a lot of atom percent. Okay. This is interesting, and this will be important in a minute because I'm doing a line sample from this point to this point across this very broken up structure. It looks like it's broken into three. It's spat out its guts here and its subguts. So that is a wheel that was in here, and that is a wheel that was in here possibly. Okay, and it's really died and buried itself in, and it's kind of like all came out of phase at the same time, out of coherence rather. Now the interesting thing is that the phosphorus, as we track across here, there's no phosphorus basically. It's all the way down here. No phosphorus, and as we hit the boundary here, the phosphorus shoots up, wow, way up there. Look, okay. As we come off this edge here, it drops way back down to background again. Okay. Now what happens as we come up here? The copper, as we get to this point, drops. It drops all the way down, but we still have some copper, and then it comes up gradually over here. And part of the coming up gradually is because you're actually able to, the electrons are able to go through this surface material and see the copper atoms underneath. Now what's interesting is there is some sulfur here, but the sulfur is predominantly at the top of the structure that died. There's a concentration at the top. You can see it's kind of like up and down, and then it goes up here at this top area here. Okay? And again, the oxygen comes down. Now, as the phosphorus goes up, the carbon comes down, and so does the oxygen. That's going to be very important later on. Again, another one buried itself sort of slightly on a tilt into the surface. This one's got a very smooth outer boundary, and I can't work out whether it became smooth as it decohered and burrowed into the surface, knocking off the spiky bits, or it was just quite densely packed inside. Okay, but whatever, you can see the green area down here is basically phosphorus. Okay, and you have carbon and oxygen. So carbon, oxygen, phosphorus, and we know there's copper there. Very consistent pattern. With this one, I'm just looking at the carbon, oxygen, and the phosphorus and the copper. You can see the copper's everywhere in the background, and a little less here and a little less here. But the oxygen, the phosphorus, and the carbon is mostly this splodge coming out of this one, out of one pole of it. and this stream that probably came out of this pole. This one here. But definitely the phosphorus is only on these outsides. Okay. So was this seen by anyone else in the past? What do you think? Do you think it was? Anyone can make any guesses? Who might have seen this in the past? And in what kind of coherent energy transformation systems that might have been? Any guesses? In Egypt. Well, that's an idea. Yeah. Not thinking along those lines. I'm thinking of researchers in the past. Not regions of the world. Monks, maybe. In people in India, quite possibly. Less of the countries, more of the people. All right. We're on the wrong track. Matsumoto, yes, you get the prize. I don't know what it is yet. Senxie, yes, Matsumoto. Okay. Matsumoto in 1991, in observations of heavy elements produced during explosive cold fusion. In the experiment, he had heavy water, D2O. He had sodium chloride as the electrolyte. He had a palladium electrode and a platinum counterelectrode. Now, from gas mass spectrometry, he saw 3 helium or tritium at mass 3. 19, he saw fluorine, which we've just seen, but this is gas mass spectrometry, or possibly basically OH, but it's OT. It's oxygen with tritium. So you can see it here, fluorine or oxygen with tritium. And then potentially at 20, he's seeing neon or possibly D2O. Now, look what he saw on EDS. He saw fluorine, we saw that in Benjamin Huang's system. Magnesium, we saw that. Aluminium, we saw that. Silicon, we saw that. Phosphorus, we definitely saw that. Sulfur, potassium, calcium, titanium, iron, copper, and zinc. Now, he had a heavier element than copper. Okay? He had palladium and platinum, both far heavier than copper. But if you exclude the fact that he saw zinc, we saw every single one of these elements in the products. Absolutely every one of these products. So let me go and find his paper now so I can just show you. And it's quite ingenious, and this will be a method where we can analyze material using his approach here and get the gases out. Now, if you remember, I did an experiment with Alan Goldwater at his Magic Sound Lab in California, where we looked at 3 gas collections from Henk Uren's Vega experiment. And we determined that it was producing potentially even fluorine gas, but also it was producing heavy oxygen isotopes, and it supports the observations of Benjamin Huang predicted by my good self. There we go. So here, this is the paper. It's reference 19. It is page 123 in the book. And observation of heavy elements produced during explosive cold fusion. Elements such as sodium, magnesium, aluminium, and zinc are observed inside grain-shaped defects. Now, what he did was, this is a standard type of, this is cold fusion 101. Cold fusion 101. Palladium deuterium experiment. Okay? Palladium deuterium experiment. So, what he did actually to do this gas analysis here was, if I just zoom this down a bit, he took the electrode and he heated it. He heated it at 175 degrees and then raised the temperature over a period of 2 hours, or rather over a period of an hour, to 775 degrees C, and then kept it at 775 degrees C for 2 hours later still. And so essentially what these elements are that were caught in the gas analysis are off-gassing from the electrode, right? They are off-gassing from the electrode. So this is something, and I've sent an email to Binchuan Huang saying, can you grab a load of detritus and then apply this process to the detritus and see what gases get evolved? I don't know why I didn't think about this. This goes to show the genius of Matsumoto yet again. And of course, you can see as he is degassing this sample, these signals that he sees here all start to shrink, okay? Until the signals here are basically not there in this middle range here. Absolutely brilliant thinking. And then he's looking at various areas on the electrode and he finds a range of elements. I didn't actually list this in here, but he's found, obviously palladium is in there, but he finds indium and ruthenium. But of the other elements that we're discussing here, you can see you've got the sodium, magnesium, aluminium, silicon, sulfur, calcium. And here down here, you've got iron and zinc and phosphorus here. Okay. So Matsumoto submitted this paper to Fusion Technology on March the 19th, 1991. So yes, there have been people that have observed exactly the production of these very same elements. And the first up was Matsumoto in 1991 in a cold fusion 101 experiment. When I said in my poster presentation at ICCF 26, I don't think LENR is really just fusion. It might be cluster decay, or it might be matter collapse and rebirth. I absolutely think it is those things. He is not the only person that saw this. We also have Ficcardi and Piantelli in their 1994 experiment. Other experiments as well, but I'm just referring to the 1994. Why? Because this was the most heat-producing reactor that they produced. And this particular electrode, this pure nickel electrode, it was nickel with nickel deposits on it. It was an electrode that I had the pleasure of holding in my hand in late 2014, early 2015, when I had the honor of visiting one Francesco Piantelli. And this is from a paper called Overview of Hydrogen Nickel Systems, Old Experiments and New Setup. So he was reporting on the data from 1994, but in this paper published in 2000, he said we found fluorine, sodium, magnesium, aluminium, silicon, phosphorus, sulfur, chlorine, potassium, calcium, chromium, manganese, iron, copper, and zinc. Apart from the light elements which are not detectable by SEM, i.e., he's saying the things that I said earlier, things like boron, beryllium, and so on. You can't detect those elements. Lithium, you can't detect those with SEM. So essentially, I predict that those will be also being produced, however you don't see them. We found all the elements lighter than nickel, all of the elements lighter than nickel. So nickel was the starting material, and they had hydrogen in there. Nickel and hydrogen. Plus, they found copper and zinc. Okay, this is cold fusion 101 nickel-hydrogen system. So we have the exact same species of elements found, and none of these are fusion. You can argue that zinc is fusion. It's you throw a proton into copper and you get zinc, or rather, copper and zinc are both fusion. You keep throwing protons into nickel and you end up with copper and zinc. Okay, but these are not fusion. They are not fusion. They are not fusion. This is in cold fusion, so-called 101 nickel-hydrogen system. This is Matsumoto in 1991. Cold fusion, so-called 101 palladium deuterium. There we go. So this is coherent energy transformations. This is matter collapse, cluster decay, matter rebirth. Now let's have a look at what that electrode showed. This was reported in 2006, and I am still deeply honoured to have handled this electrode post this date in late 2014, early 2015. This is the nickel electrode at scale 200 microns, 50 microns full width, and 10 microns full width. And it's basically continuous across the whole mass. And then here, this is the sample rod at 200 microns, 50 microns, and 10 microns. In particular, darker zones appear here and there. New structures similar to broken bubbles arise. And then I looked at this and I thought, you what? You what? Look at it. What do I see here? What is that? What is that? I'm shaking my mouse. Can you see it? Can you see it? What's that? What's that over there? What's all this guts spilling out over here? What is this? What is this guts here? Okay. This is where the new elements are. Okay. And it's got a ball in front of it. What? Seriously? Here's a close-up. Now, I want to write to the author and ask them, have they got, or any of the authors that may still be alive and have access to the data, have they got higher resolution images than the ones that were in the paper? Because these are not high resolution images. Okay? Yes, David, I expect this is an iron-rich crenellated microsphere. Yes. And it's spewing out of the back. And this pattern, it's not just that I recognize this and this spray pattern. I mean, this spray pattern is basically identical to a spray pattern in Matsumoto's book. Look, and we've produced the same thing. Look, spray pattern from a ball, in this case a lead ball. Look, there we go. Right, let me go back. Can you see? Can you see? That there, that over there is the same. Okay? The same. And this is also interesting because it says similar to broken bubbles arise. Okay? Well, what did that remind me of? Well, that reminds me of these. These are tracks cutting through the zinc. Because zinc has a low boiling point and it boils out of brass and it went in between the two plates in the Vega Valley. This here, in my view, is identical to this. And do you know what we have at the end of these trails? We have a big ball. We have one of these balls at the end of the trails. I'm going to show you. But before I do that, look at this. This is Matsumoto's carbonized film. This is the carbon and carbonized film containing iron. Now, is it in the iron or is it in this ball down here? Is it in this ball down here? I'll get rid of my mugshot. Here, this is from the Vega Valley Eastern Plateau. And I'm going to zoom into this in a second, but you can see at the end of each of these trails of carbon, you have an iron-rich crenellated sphere. Okay? So I'm just going to go and zoom into that. I will come out of that and I'll go into here. And we'll have a close look at that. Okay. So this is the kind of carbon, silicon. These are all the elements that come out of these systems. But here you go. There was a ball here, there was a ball at the end here, and the material is spinning around it. But when I hit the electron beam, the ball jumped out of the way. Here you can see a ball. This is probably where the hole is, and this is where the material is spewing out. It's coming around this way. Okay. Let's go up here. This is actually an iron sphere with a vortex helix of iron, and this was where it was interacting with the top plate. So this is almost an iron core. This was actually, this here was the first toroidal calcium oxide object that I found. Let's see what we got up here. And there we go. Again, the material is swept around. It's spinning around and it died as this iron-rich crenellated sphere came to its demise. Again, another one down here. Material spewing out of the bottom section here. Okay, so there's another one down here. Look at this. This actually is... oh no, it's not this one. It's a different one. It might be the same one. Yeah, this is the one with the... what happened there? I've lost. I'll move that. This is actually the full vortex one. So you actually have the tornado tube here coming in. This is the top of the caduceus. This is the substructure sphere shooting out just inside the golden ratio line. And this is the core, and that is the back of the core where the material is spewing out. Okay? It has a hole here, and that hole would butt up to the top of the caduceus here. So there's a vortex hole that goes all the way through here, and it goes into the sphere that fits there. Okay? Just to show you, this is the paper by Campari, Focardi, Gabbani, Montalbano, Piantelli, and Veronese. This is a pseudo mock-up of what the experiment was. And the one I'm referring to is this one. It's the only one that produced neutrons, although it didn't produce neutrons directly. The neutrons were produced by the interaction of proton with a vanadium-50, which led to a reaction that caused the emission of neutrons from the synthesized elements. Okay, it wasn't from the main core of the experiment. They had a total excess heat. It was the most heat-producing reactor, and it was from September 1994. They actually had to shut down the lab for 3 weeks. It ruined all their neutron moderators and so forth. So, so the sample that we were looking at was from 1994, and this is the same sample producing emissions of protons, and I would argue that these protons are being emitted from charge clusters that are inside the metal, and they're breaking up and they're spitting out protons and heavy ions. So here's one of the SCMs finding most of the elements in this particular spot. Okay. And here they're saying we found fluorine, sodium, magnesium, aluminium, so on. So basically, they found all elements lighter than nickel. So that's the phrase that I copied there. Okay. And then this is the image, which was what they actually found the material in, which I showed you here. Okay. Okay, so moving on. This is from the Vega Valley, and this is also from the Vega Valley, which I've shown many times before. Materials spewing out, mostly carbon and oxygen, a little bit of sulfur. And the other material that's coming out here, we've got titanium, aluminium, calcium, silicon, and so forth. So same kind of signature material coming out of the pole. Now, more recently, I have been sent this paper, which is from the Bogdanovich team, Nesterovich, 2019. We've discussed this before. This very, very specifically talks about the formation of a monopole, what they call a magnetic charge. A magnetic charge from a pinch plasmoid, the pinch effect of the plasmoid. So it says scheme of a plasmoid formation in the zone of magnetic charge localization with a trail of electrons. BE, this, is the electron flux magnetic field line. The B, this overall, is BE plus BM, the magnetic monopole charge. And so BM here are the field lines of the magnetic charge. So this effectively creates a magnetic charge. That is their model. But they are showing this particular iron-rich crenellated sphere, in my view. And it says here, spherical growth and thread on the blade surface after periodic discharge in liquid flow near the substrate. It says substantial evidence in support of this hypothesis, that is to say the formation of magnetic monopoles, may be provided by the spherical objects with a hole on the axis. Not a hole, not two holes, a hole on the axis, found in significant numbers in the post-discharge period on surfaces covered with tracks, trenches. They are considered to be cooled plasmoids with an axis of symmetry coinciding with the axis of rotation. The axis of rotation would be through here. The axis of rotation would be through that hole. This is the axis of rotation. I agree. You can even see that it laid down this material almost little like a spiral coming out of there. All of these has an axis of rotation. And so you can imagine that this is wound round here, this is wound round here. So this would be the axis of rotation. It's underneath there. And it's probably binding itself to the copper substrate. As this came down here, it's rotating. And it's flailing around and it's producing these tracks. These same tracks that were observed in Cold Fusion 101 nickel hydrogen system from 1996. Which produced all of these elements here. All of these elements. Again, Matsumoto, now in this case, the plasmoid, the plasma toroid, created a sphere of lead, but out of that lead sphere came predominantly carbon. Predominantly carbon. So I've highlighted and talked about phosphorus many, many times in this presentation. And you might like to ask, where can the 31p phosphorus, it's a single isotope, 31p, where is that coming from? Well, on February the 13th, 2024, and this was prior to the very first analysis of Binzhen Huang's cores, which occurred on March the 11th, 2024, I had predicted, based on known decay rates, that the Kladoff detections of beta and gamma in his reactor after deliberate addition of CO2 was due to the formation of 31 silicon from 13 carbon and 18 oxygen. It could also be produced by the fusion of 14 carbon and 17 oxygen. The 31 silicon decays to 31p. I also say here that in addition 31p could be directly produced from the fusion of abundant 14 nitrogen and mostly synthesized 17 oxygen. We've proven that 17 oxygen gets synthesized in these systems from EDS, from gas analysis, from Vega plasma based gas analysis, and from the analysis of Binzhen Huang's reactors with many different systems, both EDS and by mass spectrometry. So this could be a way, but you've only got the dissolved nitrogen in there. But that wasn't the way that Kladoff was doing it. I'm going to go and look at Kladoff's paper now. So we need to have a look here. And we're going to look here. So this isn't the pattern. This is me analyzing how he observed, because Binzhen Huang wants to show in the next paper, which we want to publish in Nature, that we can observe the production of radiation from the system. meaning it's doing something more interesting than just showing, what do you call it? How should we say? Detritus or concentration, yeah? Right. So you can go and see this. It's called Ultra Method for Obtaining Energy. And you can see here that I say that he gets his extra excess heat by adding aluminosilicate suspension because of these fusion reactions. Aluminium and aluminium goes to iron, produces all this energy and so forth. But he added carbon dioxide here and saw gamma and beta radiations. And he saw this decay rate, which comes down to 8 hours. Okay, and so if you work out the half-life, it's essentially has to be, the only one it can be, is silicon-31. And so this is your silicon-31 here, decaying to phosphorus-31 with beta particle. The energy is 1.491 keV, so you can see beta particles quite likely. And also, you will also see gamma because the beta particles will do Bremsstrahlung radiation and they will produce gamma energy photons. Okay, so I worked out that essentially the half-life is the same and so forth. So I worked out essentially that whilst he didn't say what the radioactive isotope was that caused this half-life, it has the same half-life, and therefore it must be that, and it's from the fusion of carbon and oxygen. Okay. So I've suggested that he adds, ideally he boils the water and then he adds carbon and oxygen, CO2 to the water to see if you can get that radiation signature. Okay, so you can go and look at that on that link. Now, how is it getting it? I'll remind you how it's getting the carbon and oxygen in this state, but also how it would feed itself. We said there's two ways it can feed itself. It can grab material from its surroundings. And I believe that if we have a very fast camera on this Vega experiment in Prague, and there is someone out there that very kindly said, well, I do have some phantoms or something. It would be great because it would be global shutter and it would be nice to see. We know this is spinning around like this. It'll likely be either going up or down. That's the only, two ways it can go. And if that's the case, it will strip material. Now, I think that if a plasmoid is traveling in front, it's going to be grabbing it from the North Pole and punching it up its arse, like I call it. It feeds itself through its arse. So it grabs material from the environment and feeds that into its core. And that gets circulated around and around and around. And some of the proportion of that gets captured into the core and is cohered into coherent matter in the core. The problem with having your anode here is that there's no central bit for it to go into, unlike a wind hex. So the question is, should we be having a core with a hole in it? Should we be having a core with a hole in it? Because, we need to think about the arrangement. I mean, do we have the electrode support coming off from the side? Okay, and a hole in the top and a hole in the bottom. Would that be a good thing to do? Yeah, maybe a ring anode. Maybe a ring anode would be a very good approach. Definitely something to think about, Gordon. I kind of think it should be a sphere, but a torus is also good. A torus would be better from the point of view that most of it would be low surface curvature, Whereas if you had a hole in a sphere, you're going to have high surface curvature on the actual hole. So I think we should be trying a ring anode. And to a degree, that's kind of what we did when we had spiral coils in there. Okay. So let's go back to where we were. It is feeding itself from the sides and from the bottom through the vortex core. This explains how it can burrow through alumina, how it can burrow through silicon dioxide, and it also shows how it can make tracks. The tracks that have, and I will do a deeper dive onto this to spell it out, but the tracks in my view that have crossways tracks are 2, 3, possibly even 4 subtor structures that are moving along the surface, leaving a main trail and small cut trails as the beams come through the non-radiating boundary of the main tor. Okay, that's what I think is going on there. Okay, so it feeds from the side and it feeds from the bottom, and ultimately all of the stuff ends up going in its bottom. And so what we know from this analysis is that most of the material inside is carbon and oxygen isotopes. Carbon 52.23% here, oxygen 30%. So carbon and oxygen here. Now there is a nitrogen peak here, so that could be a good proportion of the material in there as well. Maybe we can go back to one of the other ones which had a where I actually clicked on the nitrogen, because there's definitely a nitrogen signal there. Let me just see if I can find which one that was. Where did I put the nitrogen signal? Nitrogen. Oh, I've got nitrogen there. Nitrogen here. Okay, so if in this one where we've got nitrogen, and that's on 231 over here, we have carbon, nitrogen, oxygen totaling 50, 60, 70, 80, 90, at least 90% of the atoms, sorry, the mass rather, in this case, is nitrogen. No nitrogen there, no nitrogen there, no nitrogen there. I mean, there is nitrogen, but I've not selected it. Okay, anyway. There's some nitrogen there. So in this case, it's 52 plus 30 is 82%. You could argue here that probably 90% of this material in here is carbon, nitrogen, and oxygen. If that is the case, and they're all isotopes, you have direct synthesis of phosphorus possible from the most abundant, that is to say 14 nitrogen is 99.63% of natural nitrogen, okay, and 17 oxygen. And guess what we produce in these systems? We produce 17 oxygen. So this system, 31 phosphorus, in my view here, this 31 phosphorus actually is a signature of the production of 17 oxygen. The other way we can get there is with 13 carbon and 18 oxygen. And the thing is, 13 carbon is a reasonable percent, 1.11%, but we're never going to get to phosphorus being, well, we are in that instance. That would account, the 13 carbon and 18 oxygen, where's the oxygen? That's 0.21%. That would actually pretty much get us to phosphorus at 0.318%. It might do that. It's a little bit off, okay? But anyway, and this is by mass. Yeah, I don't know, it might do. It might get us to that. It might be the fusion of carbon and oxygen, but the production of 31 silicon that decays to give that 31 phosphorus. So effectively, from adding even non-biomass carbon dioxide, that is to say, if you add fossil fuels, so-called, it doesn't have any 14 carbon, so you can't do this process here, okay? But anyway, 17 oxygen is even much, much rarer than 18 oxygen. I suspect that when you add CO2, regardless of its source, the observed gamma and beta particles come from the production of 31 silicon to 31 phosphorus. And we know this happens a lot in these magnetohydrodynamic systems in cavitation, which is what Kladoff did, because you see a lot of phosphorus on the outside. Okay, you see a lot of phosphorus on the outside. Now, of course, because you've got protons going in there, you've got electrons and you've got antineutrinos, you're going to get more nitrogen in here, you're going to get more carbon isotopes, you're going to get more oxygen isotopes, heavier carbon isotopes and heavier oxygen isotopes forming. We already know it forms the 17 oxygen, so therefore you could have a scenario where you are producing a lot more 13C and a lot more 18C than natural abundance. That could account for the amount of phosphorus in there. Here are some reactions, and here we look. If we're going to make, if we want to make isotopes of carbon and oxygen, we start with oxygen 17. Oxygen 17 produces carbon 12 and neon 22. This is the reaction in the paper, the scientific reports paper. Here you get oxygen 16 and oxygen 18 from fusion of 2 carbon oxygens and fission. This is a 2-2 to react 2-2 reaction. Okay, so there we go. We've got an oxygen 18 being produced, and that will give us our 13 oxygen oxygen 18 reaction. And again, here we've got oxygen 17, oxygen 18 producing carbon 13 and neon 22. So we're getting a lot of reactions that produce neon 22 at the top here, which is what we observe, okay, from oxygen 17 interactions. Okay, so my conclusion is that the fractal toroidal magnetohydrodynamic structures produce coherent matter wave structures that capture energy and matter and can transform them into the elements for life. The core elements are those needed principally for life, including nitrogen, or are the main components of the Earth: oxygen, silicon, aluminium, calcium, titanium, and iron. If you look at what the Earth is made from, it is almost entirely these elements: oxygen, silicon, aluminium, calcium, titanium, and iron. All of those elements get synthesized. Okay? Other than the things that we stand on and we build our houses from, everything else is produced in the core. And on the boundary, the principal elements are likely hydrogen, though we can't see it: carbon, oxygen, and phosphorus. So with nitrogen from the core and carbon, oxygen, and phosphorus and hydrogen, that is basically life. That is basically life, because phosphorus is crucial for both plants and animal life. In plants, it's the key component of DNA, RNA, and adenosine triphosphate, which drives energy transfer for growth, photosynthesis, and nutrient uptake. It's especially vital for root development, flowering, and seed production. Well, if you don't have root development, flowering, and seed production, you are basically stuffed as a plant. In animals, phosphorus is essential for forming bones and teeth. Yeah, if you're an animal like us, humans, you're pretty useless without bones and teeth as a part of calcium phosphate. Of course, as well as for DNA, RNA, and adenosine triphosphate, supporting energy metabolism and cellular functions. So basically, you cannot procreate, you cannot grow, and you cannot support yourself if you do not have phosphorus. It's a critical component. Without adequate phosphorus, both plants and animals suffer stunted growth, weakened structures, and impaired biological processes. It's often a limiting nutrient in ecosystems, meaning its availability can dictate growth rates. Just not having phosphorus can make plants not grow. What does this mean? You have all of these people, Shishkin, saying, I take my cavitated water where I've had enough flux of these strange radiation birdies to kill me, right? And I feed that to my plants and it grows really well. I think the wastewater from cavitation heat systems will be an absolute gift to agriculture, because it will have nascent synthesized elements, all of the elements for life, those critical elements for life. Sulfur, probably some fixed nitrogen in there as well, and also phosphorus. Absolutely critical. I think that's when you feed this energized water that's gone through cavitation. You don't want to go through too much cavitation, because you start creating, look, we saw some cadmium in there. Whether that was real, I don't know. But we do know that from the work of Leclerc, if you keep running it through the reactor in a cycle, you will end up producing all of the elements in the periodic table. Not good, not good, not good at all, right? But a cavitation heat system where the hot water is made, it then goes through your hot water system, and then not too many cycles, and then it is used for instance, irrigation on crops. You could provide heat for a greenhouse, steam for processing product, and nutrient-rich water for the plants. This, in my view, is the flower of life. The structure, the magnetohydrodynamic structure, in the form of the flower of life. That is to say, a minimum 4, but preferably 6 or above substructures. But any of them will do. Will provide newly synthesized elements from whatever elements you give it. Palladium, platinum, uranium. I mean, if you start with uranium, you're going to have a lot of mess in there as well. So, like, probably don't do that. But even if you start with light elements, even with light elements, you get heavier elements forming. Okay? So, you know, life doesn't use a lot of nickel, but it does use iron. So if you have iron in there, you're going to get every element lighter than iron. And it's not that, people think if you make something lighter than iron, then you're going to lose energy. But if you're starting with a lot of hydrogen and oxygen, and you're making all the elements in between, you can make a lot of energy. And you can make all of the lot of elements in between. These structures do like to get stuck to iron. So maybe aluminium's the best bet, because aluminium fuses easily to iron to give you your excess heat. And it also can fission, and it's not fusing and fissioning, it's cluster decay. There is some fusioning, there is some fissioning, but it's mostly cluster decay and matter collapse and rebirth. But to see the corroboration, both in Matsumoto in 1991 and in Focardi Piantelli work in 1996, of what we are seeing in multiple systems now, which is not cold fusion. It is not cold fusion. That is a dead term. It is a dead term. Okay? It's coherent energy transformation. There's all kinds of things going on, but it needs coherence to do it. You need coherence in forming the intense magnetohydrodynamic structure. That produces the topological phase singularity, which becomes the topological monopole, and the monopoles are able to tear matter apart and cohere it into wavelets, and when that matter is ejected back into the ordinary vacuum state, it creates all of the elements you would want. Now, as it says in Sviatomenko's book, if you keep piling nuclei in there, at some point it goes past iron and it shoots up into thousands of AMU. You don't want to do that. This isn't a system you try to take to the max. Nature likes to do it gently. And as I said many moons ago in 2019, it's like water flowing down a stream or coming through a crack in the ground under pressure. Lots of cavitation, and it's a one flow through process. Animals and creatures like to live near crashing water on the shore, fast flowing streams. They like to live near hydrothermal vents. They like to live near springs. Why? I believe and have maintained since 2019 very clearly that that is because these are the places where nascent bioactive elements are formed in a very easy to absorb way. They're not chunks of iron, they're not chunks of phosphorus. They are actual phosphorus atoms that are easily absorbed. Okay. So with that, I will see if there's any questions, and I might have a little bit of crazy for you. I think MHD has been very much aware for a long time by many people. Well, certainly a Fountain of Youth from the point of view that there will be embedded energy clusters in there, plus all of the nutrients you need. Yes, Gordon, this is the equivalent of the PC versus massive mainframe. Yeah. If you're living in a place where there's a lot of water, this is a no-brainer, an absolute no-brainer. Dennis Matovich said when doing these experiments, was AC HV used or DC pulsed? In the cavitation experiments of Binger and Huang, it was a injector that produced the initial hydrodynamic vortices. He doesn't know, but I explained to him that his rifling on his inner tube, combined with traveling down a very long path of tube, produces helicity in multi-axis, that is multi-axis shear, which spins and spins and spins these structures up so that they organize into these structures that do the work. Okay, so there's no discharging in there. There is charge separation and magnetohydrodynamics formed from the polar nature of the water in the hydrodynamic structures that get formed. In the case of Piantelli, there's no discharge, it's just heating and it's resonance. The actual structure that did the work was a few millimeter section in an 8 centimeter rod. What it doesn't show in his patent is that the heater wire is tightly wound at one end and it stretches out. He told that in a personal one-on-one session, which I revealed in ICCF 22 in 2019 as well. And that produces a thermal gradient, and so there's a phonon resonance in there that triggers the effect in that nickel hydrogen system. In the case of the system of Takaaki Matsumoto, it was AC, but short explosive pulses. So there were discrete discharges, and he had an SCR attached to a variac. There might have even been a bridge rectifier there, so it might have been pulsed and sinusoidal, but only half of the sinusoidal curve. But very short pulses, just a few pulses typically in his experiments. Anyone know if you can do this stuff at home and try it in the garden? Yes, you can. Yes, you can. You can make a cavitator. I mean, if you're not concerned about the excess heat, then you can make a cavitator. I wouldn't stand near it whilst it's operating, even if you're not, even with just straight flow through. Yeah. Thank you, Screwdriver Tuning. How did your pyramid test go? Well, I haven't been in the lab much, but I have got the film exposed. I don't expect to see much on that film, but at some point, either later this year or next year, we will put in the active structure. So I'll run through a brief review of what we talked about today, and then I will do a little bit of crazy. So this was day Flower of Life 2, and we looked at this dog, this lion dog from Japan. We looked at his face with the vortex and the anti-vortex, and the point in the center, this kind of sphere with a hole in it, and this nostrils with the two things coming up, the spirals that would go in there, the coherence of two streams of matter. But under his paw, we see a smaller version of the Flower of Life in the form of a sphere, and I'm calling this the microball lightning. Facing the north side, and there's one on the south side, there was a pin running through the center of the building, and looking into that, we see it is vortex and anti-vortex with the focus beam, like a little mushroom, and this for me is equivalent to the Boyd Bushman monopole beams, or magnetic beaming patent that he got awarded when he was working at Lockheed Martin. And if this was a strong north, then this would be a strong north beam, a topological monopole of north type. And if these were south, the corollary. We looked at these structures from Benjamin Huang's inner pipe and inside of the outside pipe, seeing that they had these wavy-like nature to them, and that they could capture material from the substrate in a very thin layer. So it's kind of like this doesn't extend far, but it's incredibly powerful. It's almost amazing to consider that something moving around in water can literally skim off a chunk of copper and wrap it round itself. It can also skim off through the disruption beam that comes down the bottom, and when the matter is deconfined, it will spew out, also in a tornado or a tube like this. This is just its guts fully spilling out. This is where its pressure was enough to break the structure up. Now, we're going to, with our little bit crazy, I want you to hold this in mind. The idea that the outer structure can be very powerful, but if it's disrupted, it can break up and the inner structure come out. And we've seen in other things from my presentations with regard to this material from Benjamin Huang, that substructures are within these bigger structures. Okay. And this is a core completely free. I believe this is a 3-tor structure inside, but it's these wavy outside areas that are in layers. You see, that intrigued me when I saw the same thing occurring in 1/8000th of a second freeze frame from the Vega experiment by Jan Rack in Prague, which people will be able to see next week or the week after in operation. I think this is a prototype of what this is. This obviously is only 10 microns or something across, whereas this is much larger. This is in the multiple centimeters across. But I think it's trying to do the same thing in my view. And we've seen 3 in cavitation here before, and the beams come out. Okay. But 6 is what gives us the Flower of Life, as we did in Flower of Life 1. Now, looking at the elements here, we have copper, oxygen predominantly, with sometimes a little bit of carbon, which may have come out of the systems. But inside the cores, we have all of the elements below copper, except for manganese, chromium, vanadium, and scandium, and cobalt. Cobalt, and nickel. We just don't get those, but we get the others. And that goes on for many, many different samples, different areas. Okay. Again, this one blew up. This is a subtor that's come out from inside here. We've seen these, and here's a subtor probably that's come out from one of these. So this is a little micro ball lightning inside a much bigger ball lightning. Now on the outsides, it's typically carbon, oxygen, phosphorus, and copper. Okay, very big peak of phosphorus here. And it looks like from this band that if you trace across, it is when the oxygen dips and the carbon dips that the phosphorus goes up. So there's kind of like a correlation between the two, and it may be that it is the fusion of carbon and oxygen that is leading to the production of phosphorus. Again, phosphorus is just on these structures. So Matsumoto observed the production of all of these elements that we have observed, and some of the ones that we observed in the Henk-Uranus system. And that is from cold fusion 101, as it was called, cold fusion. He calls it cold fusion back in 1991 using heavy water, sodium chloride, and palladium platinum electrodes. Ficcardi and Piantelli in 1994, a few years later, reported in 2000, found exactly the same elements, but this is in a nickel hydrogen cold fusion 101 experiment. Moreover, in that exact same electrode, he saw these bubbly structures as a trail behind a ball, or a little ball with a little spewing out structure. Okay? Very, very similar to those which we've seen trails behind iron-rich crenellated spheres in Vega experiments. And that under SEM, you can see is functionally equivalent to what was observed by Matsumoto. Here's an example of the carbon and oxygen and sulfur, sulfur being fusion of two oxygens, being emitted from an iron-rich crenellated sphere. And that if we look at the two little discs that have come out of the hole, and obviously this is the hole here that emitted this material here. And you can imagine that this is rotating around and twisting. Maybe the ball's rolling along this side. These two little structures came out and inflated. These contain carbon and oxygen in predominance, in atomic weight. On atomic concentration, you're talking about 70, 85% nearly. But we've also got aluminium, silicon, calcium, titanium, iron, and there's copper and even zinc in there. Okay, but copper and zinc are in the substrate. So Nestorovich, working with Bogdanovich at Moscow Nuclear Physics Institute, reported in 2019 what they believe plasmoids produce a magnetic charge. That is a euphemism for magnetic monopole. And that the signature that tells you that that has happened is may be provided by spherical objects like the one that they took an image of here with a hole in it. There's the hole on the axis, this axis through here, found in significant numbers in the post-discharge period on surfaces covered with tracks, just like we observed here. Okay. Of course, a single hole on one side is what Matsumoto observed. And where did the 31 phosphorus come from? Well, I think the material, as I said earlier, is feeding in from the sides and from the bottom, from the sides to the bottom. And it's merging in there, and I believe that it is predominantly likely to be 13 and carbon and 18 oxygen goes to 31 silicon, and this decays rather rapidly with the same decay rate that was observed in the radiation emitting source in Kladoff's 1992 patent. 1992 patent. I believe he was producing 31 silicon that produced the decay rate that was observed, producing 31 phosphorus, which also means that Kladoff was producing 31 phosphorus. Okay, and if you start with 13 carbon, that's 1.11%, and 18 oxygen is 0.2. You might get to the kind of numbers down here that you have of phosphorus. However, if you have a system that is producing heavy nuclei as it goes through the core, heavier nuclei by adding protons, electrons, and antineutrinos, as seems to be the case, that must be the case actually, to produce oxygen 17, then you should be able to produce higher mass carbon, higher mass oxygen, and therefore you can produce more of this. And so I showed a sequence of events that does produce the neons that we observe, okay? But it requires the formation of oxygen 17 to keep the process going, producing carbon 12 and so on. You get the reaction chain that produces the observables. So the conclusion is the hypothesized reaction that I presented in ICCF 26 uses coherent energy transformations to produce all of the elements for life in fractal magneto-hydrodynamic systems, and that it produces this core nutrient in soils that all animal life depends on. Okay. Right, so what's my little bit of crazy for you? Well, it's this. Earlier this week, there was some UFO hearings. And there was this video showed, which we will have a look at. So, it started here, it's locked on, and it goes along, and it travels. And it seems to rotate a bit. And then missile comes in from another drone. We'll step through it. Boom! As soon as it hits, let's see if you can see that. As soon as it hits, it produces a perfectly spherical object, which is carrying forward and traveling through. Perfectly spherical. Okay? Now we know from our cavitation experiments that a sphere emerges from a toroid, as the structure that in the cavitation ultra experiments, the torus, as it's disrupted or the energy is switched off, it breaks away into a sphere. But this might actually just be the sphere. Okay? Now in the next couple of frames, the sphere kind of like breaks open. So we've still got a hemisphere in this part here, but we've got like a skirt, okay, here. And it starts depositing 3 objects. 1, 2, and then a third there. Okay? 1, 2, 3. This then kind of flails around a bit. And these objects start to self-organize. They're all carrying on in the same direction. This may be dropping. I'm not certain about that. There seems to be this other glow which may be in the center of mass here. This may be the control point where these are vectored around using phase conjugated scalar interferometry. So there's a point here. It doesn't quite look like the center of mass, but it's still here. Could be the center of mass. It might just be perspective. Now this is flailing around, and what I think this is essentially the skin that you see on our broken up structures. It's kind of the equivalent. So if you can imagine, we've just blown up this structure here, and we've got our subtors coming out. Yeah. That's kind of what you're seeing. These kind of blown up structures. Okay? You're seeing the fragments of the outer shell, which doesn't have phosphorus and whatever in like scratchy kind of platelets like this. It's basically a sphere, as far as your ability to discern it, and it's glowing. But the bits that bound it together have broken off, and it's become because this is made up of substructures themselves, and we know this from the cut in the hemispherical cut in the copper pipe of the Vega experiment with Hank Urine, because it has the interaction of many small ball lightnings that are woven together into a mesh. And I believe these are made in the core, and they come out and they go and get stuck on the non-radiating boundary. And that creates your ball lightning boundary on the non-radiating boundary, made up of microball lightning. And we know this from Leonid Arotskiev's titanium wire explosion, where he created a ball lightning above, and after a few milliseconds it breaks up. The surface breaks up into thousands of little ball lightnings. We know this from the Canadian video of ball lightning, that the outer ball lightning dissipated and the three structures from inside persisted. So the smaller the structure is, the more likely they are to persist for longer. In the case of the Canadian ball lightning, the outside wasn't so made up of substructures such that it would go away. In the case of Snowballs on Cobblestones video, where the substructures of the substructure of the main structure ended up by converting oxygen on the copper into sulfur, those would persist for a number of days, like the Bogdanovich work, which was part of what I referenced earlier, where you had these long-lived plasmoids moving around for 2 days on the surface. So the smaller they are, the longer they last, but you won't perceive them. It's only certain fractal levels that you're going to be able to perceive. So I think that what you're looking at there is the skin, which is semi-bound together in here. And if I go fit, so this is kind of semi-bound together. Actually, if I move that up, I won't be able to see it. Put that up there, we can go in a bit more. Maybe. Yeah, so I think what's happening here is this is the kind of skin, and it's still kind of partially bound to these things, but it's difficult to say because of the perspective whether it's actually falling, but it's still traveling in the same direction largely. But these things look like they're bound together, but they're not in the same state as they were before they came out. So the very first frame after that, boom, is a sphere. It goes immediately to a sphere. And then the sphere has a tail on it. It starts spitting out the three structures. What I will note, actually, is that if we're to believe that this is a torus this way, then when it breaks, the torus here are this way. They're orthogonal to it. Okay, the tori, subtori. This little glinting part here might actually be just another fragment of the main structure, but this is more caught into the field of these ones. Yeah. This just looks like a skin. You can see these kind of skin structures on Matsumoto's work as well when the microball lightning breaks up. So it's scale invariant, so I expect to see the same kind of process going on here. I don't know whether this is before or after. Maybe someone knows. I tried to look at the nautical miles down here or whatever. There doesn't seem to be any indication really that's good enough. And then, so we have, what's his name? There's a little glitch in here where you can see it changes between the views. Mr. Burleson to thank for this. Thank you, Mr. Burleson. But I think this is a ball lightning structure losing its skin and revealing the three internal ball lightning structures that made it up, and because they're spread apart, they're not as good. Okay, the field is much less intense, but they can still be moved around. Okay, so that's that. Well, it might be a balloon, but whatever. I'm saying in the case that it was a plasma, the behavior is very consistent with how a plasma tor made of plasma tors will be made, and the reorganization of those three structures, is consistent also, both with our experimentation and the Canadian ball lightning. So thank you very much, everyone. If there's no more questions, if there's any more questions, I don't know. I want to thank P. Atlantis for his donation, and Craig. Very, very much appreciated. Thank you very much. What happened to the missile? I think it just went straight through. It might have got damaged a bit. It chewed it up a bit. Because I think those missiles, they just spin round and try and chop things up. Do you notice one of the spherical objects is already sticking out before? No, I don't notice that. I think the interaction with the missile did disrupt it. Okay, fake leg. Okay, so this was Ode, Flower of Life 2. We have the ability to make all of the nutrients we need using a system that can be easily created in cavitation systems. And our observation in recent years is entirely consistent with those at the very beginning of what was formerly called cold fusion, both in the case of Matsumoto for the palladium deuterium system and for Focardi Piantelli for the nickel hydrogen system. Exactly the same. I think we can conclusively say this is how it works. So thank you very much for your time, and I will see you in the next video. Buenas noches, dobro noc, good night.